This is STA 381, Chapter 6, Section 6, Scatter Diagrams. All right, welcome back. We're going to be talking about another type of plot today, so I left this on the board, our mantra, plot your data. All right, so multivariate data now. Multivariate in this case is bivariate, so we're not looking at anything beyond two variables right now, but certainly we could extend it by adding some categorical values to it. There's different ways of doing multivariate data, but it does get more difficult once you get past the two dimensions. Histograms and box plots, those are univariate data graphical tools because we're only looking at one variable. So if we want to plot more than one variable, more than one quantitative variable specifically, then we have to use something else. And so in this case, we're going to do something called a scatter diagram or a scatter plot, and then investigate a statistic that's related to that. Okay, so here's a scatter diagram or a scatter plot. And so notice that we have education down there along the x-axis, and we have wages earned over on the y-axis. And I think you've seen this data set before. And so you look at this, and we look at education, years of education, and we see that there does seem to be a bit of a linear trend, but it's hard for us to see much of a linear trend because there's so many values that are down there around 0 as well. So there's, even if you have over 15 years of education, you can still be earning in amount of dollars per hour, something rather minimal. At least this was back, I think this is the population survey from like 1985. So this data is a little bit old, so you're probably thinking no one makes around $2 or $3 an hour anymore, do they? No, it's just that way back then, the cost of living was different, minimum wage was different, but you can see certainly that there's a lot of values down there around 0. But when we look at scatter plots, we still want to look at some of our basic things from SOX. We want to look at the shape. Is it a linear trend? Is it a nonlinear trend? We want to look to see if there are any outliers. We see a person probably making about $14 or has 14 years of education making well over $40 an hour. That seems to be unusual. Center is not really something that we can really tell. And spread you can look. The spread along the x-axis and the spread along the y-axis. But you're looking basically for trends at this point. And as I said, we don't want to try to nitpick it too much. We're looking at an overall trend. All right, here's another example. We have approval rating and election margin for recent presidential elections. So you see along the x-axis, we have approval ratings for the presidents, incoming presidents, or current presidents, and then the election margins. And as you can see, going from approval rating to 30 to 70, there does seem to be a linear trend. As approval rating increases, the margin that they win by tends to increase. So there does seem to be some sort of association, and we'll call it a positive association, because that just means as one increases, the other increases for these two variables. So notice we have two variables taken on each president. So that's going to be the link there. So this is like a set of ordered pairs if you want to think back to your algebra days or even your calculus days. We're looking at a set of ordered pairs. So our ordered pairs are just our two variables in this case. Here's another one. We have water quality for a sample of lakes in Florida. And we see two measurements here taken on the same lakes. We have the pH, and then we have the average mercury level. And so notice here that the trend seems to be an opposite trend, that we actually have a negative trend. So as our pH increases, and we know that pH of 7 is ideal for water, that our mercury tends to decrease. So this time we see a negative association occurring between the average mercury and the pH. Now, for our purposes, unless we're wanting to predict one from the other, you could flip X and Y and it wouldn't matter. But if you're interested in predicting average mercury from pH, which is something we'll do in a later chapter, then you would need to make sure that you put the predictor on the x-axis and the predicted on the y. So what have we been looking at in these scatter plots? We've been looking at the average pattern. So notice that we're not trying to nitpick the pattern apart. We're trying to look at that average pattern. Is it increasing from left to right, or is it decreasing from left to right? Is it a straight line? Is it a curve? Both of those seem to be fairly straight. What is the direction of the pattern? Is that pattern positive? Is it increasing? Is it decreasing? How much do individual points vary from the average pattern? So is there a lot of vertical spread, or is there not so much vertical spread? So an example, and we just saw two different examples here, but you know, if we have points lying fairly close to a line, then there's not a whole lot of spread going on. And that's a good association between the two values. But if we have, for example, points that are kind of all over the place, and it's hard to distinguish a pattern, then there's a lot of vertical spread, which is telling us that the relationship between x and y is not very strong. This relationship is extremely strong. This one is kind of hard to tell, maybe a slight negative pattern, but this relationship isn't very strong. And we'll get into the calculation of those lines, those linear equations later. Okay, so again, I'm just going to reiterate what I've said. Two variables have a positive association if as x increases, y increases. Two variables have a negative association if as x increases, y decreases. Finally, two variables have a linear relationship when the relationship seems to represent a straight line. So it could be that you don't have a straight line. Just because we keep talking about one doesn't mean all data have straight line relationships. It could be that for a while it seems to be straight, and then we get another relationship happen after a certain point of x here. And that's worth investigating. Okay, so here's another example. Driver age and maximum legibility distance of highway signs. So as age increases, how far away are those signs before someone can actually read them? So a research firm determined that the maximum distance at which 30 drivers could read a newly designed sign, and the 30 participants in the study were studied in age. So that's one of our variables, and it's quantitative, from 18 to 82 years old. We want to determine and examine the relationship between age and that distance. So distance is one, age is the other. So here's our data. So what we see is a negative association between the two variables, because as age increases, we see that the distance decreases. And that makes sense. As you get older, your eyesight gets poorer, and you actually need glasses, and you can't see as far. But that relationship does tend to be fairly linear. Remember, we're not going to try to look too closely at the relationship. The overall average pattern does seem to be a linear pattern. Okay, so is that all we can do? Is that the best we can come up with? No. So great plotter data, that's our first step. Take a look, see what kind of trends that we have going on, see what kind of spread we have going on, see if it's linear, see if it's not linear. Then we go to a statistic called the correlation coefficient. Okay, so the correlation coefficient is designated by little r, and it indicates the strength and the direction of a straight line relationship. And if you're writing this down in your notes, and I highly recommend that, you should definitely underline straight line relationship. And why is that? Because correlation is tied to the fact that the relationship is straight. You can put any two sets of variables, any two variables in there into any program, and R included, and it will spit out a correlation. But it could be nonsense if you have a relationship like this. So if you clearly have a nonlinear relationship, then you shouldn't use correlation. Okay, so it addresses the strength. That the strength means how closely those points are hugging a line. And then the direction. Is that direction positive or negative? So some properties of R. And as I said, any software is going to pull R out for you in some way or form. R is always between -1 and +1. Always. It will never be beyond those bounds. And it can include both -1 and +1. The magnitude indicates the strength, how closely those points are hugging that line. An R of either -1 or +1 means that every point is actually lying on the line. The sign indicates the direction. Positive sign means a positive relationship. Negative sign means a negative relationship. An R of 0 indicates that the slope is 0. So knowing X does not predict Y. And there are a couple different ways we can get an R of 0, or approximately 0. One of them is something fairly similar to this, where we just have points all over the place, and actually this line becomes, I'll draw a new one in a new color, something like that. Something very, very close to 0. Another way is to get something like this, where we have this relationship where the direction is changing, and so that would produce an R that is fairly close to 0. And so, again, what we're looking for is a relationship. So let's go back to our variables. We have these two variables, the age and legibility. And if we have something that is hugging a line, that's saying there's a really strong relationship between age and distance. If we have points that are all over the place, that's telling us that there really is no relationship between age and distance. So that's what you need to always go back to. What is the context of my data? Don't just spit out an R is 0.39 and be done. And so we're going to look at a couple different correlations. Okay, so notice the first one on the left is an R that's near 1. It's not 1 because the points don't all lie on the line, but it's something that's fairly strong. So we're talking in the 0.9295 range. The second one, we have an R that's near -1. So again, -9.92, -0.95, something like that. Third, R is near 0. No linear relationship between X and Y. And again, another R that's close to 0. And so the question that we usually get as statisticians is, what is a good R? What means good? Strong. What's good? Well, certainly anything that is above 0.9 or less than -0.9 is considered to be pretty strong. Between that, you can look online and you can see some rules of thumb. You'll see some, 0.7 to 0.9 would be moderately strong, and so on and so forth. But part of it is context. So context is pretty important in knowing your data and knowing your field. If you're in the engineering field, you probably want really high correlations because you want to be really sure that there's really a really strong relationship between two variables. But I've had people in social sciences say, hey, we're really happy with an R of 0.5 because human variability is so wide that if they see something in the 0.5 range, then they're excited, they're tickled to death. So it really depends on what type of field that you're in and really knowing your data and consulting experts in your field. All right, so we've learned about all sorts of different types of graphs. This is one of the ways that we can display data. And as I said, it's just one of the ways that we can display our bivariate data. There's other ways of doing it too, but this is the conclusion of the lecture.